Hello, sir.
Yes. Yeah.
So
Yes.
I'm having only one doubt on the first page that we have to prepare.
Mhm.
You have written journal, article, references, and date to be written.
Yes.
So if we cite any paper or if we take any reference of that bibliography, normally it came in a single line. So do you want it to be put it means specific that this is the journal number, this is volume like that?
No, what is the first page? No, first page of report. Am I right?
First page, yes. So after
Yeah.
title, we have to write the journal, publication, date, and page number
Yeah.
of that
Date,
particular
year, basically
article.
year. Okay. Date won't be
Year,
there.
yes.
Year. Yeah.
So I was just asking, means, do we have to put it in a specific way, like this is the journal number, this is the volume, this is the year, or this is the page number, like that?
Yeah. It should be like one line. Okay. Single line is fine. Okay. That's not.
Single line is fine, no?
Yeah. 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 All the details in single line is fine.
Okay, and we can add the institute name, na? Indian means our college name there, na?
No,
Apart
it's
from
not
that, we have
required.
to.
There is not required. Only your roll number, name. Okay. That's also.
Okay,
Okay. But just what I wanted to know the others details. Okay. Who are
okay,
the
okay,
others? Okay. Of the article what okay, assigned to you.
okay,
The article
sure.
which was assigned to you, it should have okay all the okay the initial the first title page basically. It's called title page of a journal.
Okay, okay, sure, sir.
Okay, so regarding term paper present today, I think last date. I guess am I right? Today is the last date for the term paper report submission.
Yes, sir, today.
Yeah, please upload. Okay, there's no okay. I don't entertain any late submissions. The second thing regarding term paper presentation. Okay, so for example, there are two students in a team. Two students have to present equally. Okay, so that means actually equal contribution. For example, it is 12 minutes, 6 minutes by one student followed by second student. Okay, it should be like a continuous. Okay, it should not again come back. The first speaker should not come back again. Okay, when you present it. So in the 12 minutes presentation slides, okay, 6 minutes by one student, 6 minutes okay by another student. So equal contribution should be there. If it is a single student, okay, allowed is 12 minutes. Single student, okay, if it is a single student, allowed one is a 12 minutes, followed by 3 minutes. 12 minutes is a common per topic, per a term paper topic, whatever given, term paper title, whatever given. Okay, 12 minutes is the fixed time for presentation, plus 3 minutes discussion. Afterwards, okay, now for example, there are two students in the team. One student will exit, again, okay, join after 10 minutes. Okay, one student will be okay the vivas will be conducted for one student, then followed by the second student of the team. Okay, so it may take a maximum of half an hour. Okay, half an hour plus 15 minutes total, 45 minutes. Is it clear? Okay, if it is only
Yes,
one student, then it will take only 10 to 15 minutes viva examination. Okay, plus 15 minutes presentation. 15 minutes presentation. Okay, 15 minutes has been devoted for presentation. 15 minutes, maximum 15 minutes for a viva examination for a student. Okay, is it clear? Any doubts? So Rubal, are you there? Rubal and
Yes, sir.
so I think you filled in the Excel sheet, okay, for tomorrow, okay,
Yes, sir.
slot. So since no other slots are available, you filled it, or actually you wanted to have it tomorrow itself?
Sir, I want to have it tomorrow.
Tomorrow, both of you want to have it tomorrow itself. Okay, fine. So prepare, okay, entire syllabus, whatever, okay, taught till today, okay, for the VIOS examination.
Okay, sir. PPT is from term paper only.
PPT for term paper, 15 minutes, okay, together for both of the students. Okay, 15 minutes for student, okay, VIOS examination.
Okay, sir.
Okay, so you fill it for 12:15. Am I right? I think that's what the slot, I guess.
Oh, yes, sir.
Okay.
12:52.
Yeah, both of you must be there on time. Okay, using same okay link, same Google Meet link. You have to join. Okay.
Okay.
Okay, entire syllabus. Okay, the questions will be asked from entire syllabus for the VIOS examination. Okay, any more doubts here? No, I think before starting my today's lecture, let me share, okay, my lecture slides. Okay, so if there are no other doubts regarding term paper presentation Viva's examination, let's start today's lecture. So as far as what we discussed, okay, in my previous lecture, so the one lecture has been devoted towards, okay, to have understanding about superplastic deformation. So a material, okay, some materials, okay, under certain conditions, deformation conditions, can exhibit, okay, very large uniform elongations under tensile loading conditions. Typically, if it is greater than 400%, okay, we call that deformation is called superplastic deformation. Superplastic deformation. So this kind of phenomenon has been observed in wide range of materials. Okay, metallic materials, okay, ceramics, intermetallics, composites. There are various types of, okay, materials do exhibit very large, okay, elongations, provided that there are certain, okay, if the material meets certain requirements. So the requirements for superplastic phenomenon are basically elevated temperature, high temperatures, fine grain size, stable fine grain size, high strain rate sensitivity, and resistance to cavitation. So these are important, okay, conditions the material should exhibit, okay, so that we can see superplastic deformation in materials. So then actually, if we talk about, okay, characteristics of superplasticity, if you deform material at elevated temperatures, okay, usually typically the materials, okay, follow this kind of constitutive equation, high temperature constitutive equation at low stresses. Under low stresses, this is a typical constitutive equation what we see when creep and superplasticity, okay, in both the cases we do see this kind of constitutive equation is valid. So if we talk about characteristic features in terms of, okay, if you make a plot, stress versus strain rate for a fixed at a given strain and a temperature at a given strain and temperature. So typically the stress is going to vary in this, okay, S-shaped kind of curve. Whereas ductility or strain rate sensitivity as a function of strain rate vary in the form of a bell-shaped curve. Okay. So the important region, there are three regions, region 1, region 2, region 3. Region 2 is the superplasticity region. Okay. So region 2 basically is, okay, coming from high contribution from strain grain boundary sliding. So grain boundary sliding is going to contribute to the large strains, the large amount of strain can be obtained. Okay. So, but when there is a grain boundary sliding in a material, okay, there will be, okay, discontinuities are going to generate. So those discontinuities have to be, okay, okay, has to be minimum. Then only you can get a large elongations. So that minimum discontinuity can be obtained by having some accommodation mechanism. So the accommodation mechanism, typically it can be a diffusion creep or can be a dislocation creep. Accordingly, we do see two different type of mechanisms, lift sheet sliding and Rashinger sliding. Okay. If grain boundary sliding is getting accommodated, okay, okay, basically accompanied by, okay, diffusion creep, we do see lift sheet sliding where grains are going to get elongated. Okay. If grain boundary sliding is accompanied by, okay, dislocation creep, okay, we don't see much change in grain shape. Okay, that is called Rashinger sliding. Okay, so I think these are the things we had discussion. Then we also had a discussion about, okay, effect of grain size. So typically with a refining grain size, we can get high strain rate superplasticity. High strain rate superplasticity basically means greater than 10 for minus 2 per second. We usually call high strain rate superplasticity. If I want to get high strain rate superplasticity, okay, one has to refine the grain size. But at the same time, that fine grains has to be stable, okay, at deformation temperatures. So then we can get large elongations to failure, okay, large elongations before its failure. Okay, so I think this is about the superplasticity what we had in my previous lecture. Are there any doubts? Are there any doubts of, I think, the superplasticity? Okay, so if there are no, I hope I'm online.
Yes, sir.
Sir, you are online.
Okay, fine. Okay, so today's discussion is basically related to dynamic deformation activities. Dynamic deformation activities. Okay, so if I take a polycrystalline material, okay, assume that it is an equiax structure. If we deform the material, okay, it can have a deformed microstructure like elongated grains. Okay, so when these have a deformed microstructure, okay, if we heat it to some temperature, it can undergo static recovery. That means whatever dislocations have been generated within a grains can get recovered. Or we may also see recrystallization of the grains. Okay, we can get a fully recrystallized structure can be obtained. Or we can also see during deformation, okay, when you deform a material polycrystalline equivalence microstructure, it will undergo, okay, typically elongated microstructure. But this elongated can recovered during deformation itself, or can also undergo recrystallization. Okay, you can get a fully recrystallized microstructure also. Okay, so whatever, okay, recovery, recrystallization, these are phenomena which can happen. If they happen during deformation itself, okay, we call them dynamic deformation activities. Okay, dynamic recovery and dynamic recrystallization are dynamic deformation activities. Okay, okay, and deformed microstructure, all are actually whatever changes happens during deformation, okay, those are called dynamic deformation activities. So when you deform material at elevated temperature, high temperatures, okay, above 0.5 as a melting point, one can expect during deformation itself, we can see recovery and recrystallization. So these are called restoration processes. Okay, dynamic restoration processes. Okay, for example, if I deform a material under tension, okay, or compression, whatever. Okay, so when you deform a material, okay, depending on temperature and strain rate combination, and depending on microstructure of the material, okay, we may see work hardening, or we may see work hardening plus, okay, dynamic recovery, or we may also see work hardening plus dynamic recrystallization. Okay, so these are typical, okay, curves, okay, stress strain curves, okay, of different phenomena what is happening in a material. If there is only work hardening, okay, we do see strain hardening phenomena. Okay, only strain hardening or work hardening. Okay, if a material undergoing some restoration process, okay, dynamically some restoration process happening like recovery or recrystallization, okay, we do see the kind of typical curves what we see. Okay, the stress strain curves are going to be different. So these are like a typical characteristic curves. Okay, for a work hardening plus dynamic recovery, we do see like this. For work hardening plus recrystallization, we do see a peak followed by drop, then again steady. Okay, stress as a function of strain. Okay, so these are basically as far as dynamic restoration process are concerned. Okay, for plastic during plastic deformation, we do talk about dynamic recovery and dynamic recrystallization. These two come under category of dynamic restoration process. Okay, so coming to dynamic recovery. Okay, so dynamic recovery, the stress strain curve will be like this. Okay, so what does it mean? Okay, initially there is a work hardening followed by a, okay, there is a balancing act. Okay, there is a balance. The stress is basically become almost saturated, getting saturated, steady stress state. You are seeing. What does it mean? Okay, there is a recovery and, okay, dynamically there is a recovery and deformation. Okay, work hard together. Okay, so there is a balancing thing happening. Okay, so that lead to this kind of, okay, steady stress state condition with increasing strain further. So initially that strain hardening because of dislocation density, and we do see formation of a subgrains when you form material at high temperatures. Okay, initially form cells, then those cells can convert into a subgrains. Okay, so what happens once we have subgrain structure? Okay, dislocation density becomes almost constant. Okay, and these subgrains remain equiaxed and almost have a constant mean grain size, and mean misorientation will be less than 15 degrees. Low angle boundaries. The subgrains are will be having low angle boundary character. Okay, so the mechanism, okay, by which the subgrains are going to form is basically called polygonization. The mechanism of recovery is basically given by a polygonization mechanism. For example, when you deform a material, there are a lot of dislocation density generated. Okay, and planes, if you take a planes, okay, different planes, we do see different dislocation. Okay, so what happens during, okay, thermal energy, during, because of when you have provided some thermal energy, what happens? Okay, dislocations of opposite sign are going to get annihilated easily because of, okay, easy, okay, kind of deformation activity during deformation, or even with the heat also, even with heat also, what happens? Dislocations of opposite sign are going to get annihilated, and same sign dislocations are going to form boundaries, get aligned, and form a boundary, low angle boundaries. So this is called subgrain, formation of a subgrain. Okay, so this whole process, basically can happen in the static conditions after deformation. If I take it to some temperature, it can happen. Okay, recovery can happen, or during deformation also we can see formation of subgrains. Okay, so this is basically, if it happens during, deformation is called dynamic recovery. If it happens statically, only with temperature, that is called static recovery. Okay, is it clear about dynamic recovery?
Yes, sir.
So in dynamic recovery, new grains are not getting formed.
No, only elongate within the elongated grain structure. We do see subgrains are going to form within a elongated grain. We do see, for example, if I see, here, what happens during deformation? Dislocation tangles are going to form, and cell formation forms, and these cells can convert into subgrains, So whatever opposite dislocations are there, those are going to get annihilated, can leave. The same type of dislocation can lead to formation of a subgrain. If you take a one grain, this is a one grain. Within a grain, I will see formation of a subgrains. Subgrains will have a low angle disorientation.
Okay. And that
So-
is why it reduces the work hardening process, or means
because your
further
dislocation
stress
density
generation.
has come down, because annihilation. So recovery is taking place. So dislocation density is going to return, because again we do see development of a dislocation is going to get generated, and we do see some kind of work hardening can come from this subgrain. So initially we have a deformed microstructure. If we talk about static recrystallization, or dynamic recrystallization, what happens? This dislocation is going to get rearranged and can form several subgrains within a prior elongated grain structure. This is called dynamic recovery. So if we can see the misorientation typical, if you see, on a TEM, we do get, within a grain, we do see multiple, fine grain structure, which are of a low angle grain boundary character. Okay. Is it
Hello,
clear?
sir.
Yes.
Sir, in picture number B, the dislocations that are there inside the boundaries, those are getting annihilated, right?
Yeah. See what happens. This is the kind of structure. So initially, we have one in a grain. We'll have a dislocations, entanglement with that's called strain hardening. Okay. With some amount of further strain, we do see formation of a cell structure. So these cells, within the cells, what the boundaries, whatever have, those dislocations of opposites are going to get annihilated. Leaves dislocations of a same sign that can lead to a one kind of boundary. Subgrain boundaries are going to form. So this is like,
Yeah. So the dislocations that are there inside those boundaries that are getting emptied now. So those dislocations have got annihilated, right?
yes, this is also going to get inside. If you have a some dislocations of opposition, we also going to get annihilated on the same
Okay.
plane. That's to come.
Okay.
So that leaves basically reduced dislocation density. Overall dislocation density is going to get reduced. Here we have a large dislocation density. If the subgrains form, reduced dislocation density is going to happen. However, with further deformation, what happens? Dislocation is going to get generated and subgrains are going to form. So that basically balance your dislocation density in the material during deformation. If you talk about only static recovery, most of the dislocations are going to get generated, and we will see only recovered grains. But when you talk about dynamic recovery, what happens? Again, dislocations are going to get generated. Dislocation is going to get annihilated. It's like both are simultaneously happening. That basically leads to a constant dislocation density and same stress. The stress is going to be same, because work hardening rate and the recovery rate are going to get balanced equally during deformation. Is it clear?
Sir, it always forms low angle boundaries only.
Yeah, initially it forms only low angle boundaries. The subgrains usually call boundaries within a grain. The subgrains will be having boundaries with a low angle misorientation. With more and more strain, we may see these subgrains can convert into high angle grain boundary grains, fully recrystallized grains.
Okay, okay. Sir.
Yeah.
So generally, they explain recovery, they say like it is in bending
wait.
or in tension. So
Yeah.
in what happens in compression kind of deformation?
No. See, it happens during compression, during tension also. Okay. Whenever there is a gradient, okay, that it was shown for bending is like a gradient. Okay. Whenever there is a gradient, we do see formation of it. That's the polygonization kind of mechanism has been used. But when you deform materials, compression or tension, wherever there's a gradient, that can lead to a formation of subgrains. It's a strain gradient. Okay. When you talk about bending, there is a strain gradient from tension to compression. Okay, even within a tension, okay, when you deform material, okay, we may see some gradient in that dislocation, okay, strain gradient. At some places, we may see higher strain, other places, we may see low strain. So that gradient is going to exist in the polycrystalline materials.
Okay, sir. Thank you.
Okay. Okay, so this is basically a dynamic recovery or static recovery. Basically, okay, we talk about it. If it happens, everything happens during deformation, it's called dynamic. Otherwise, it's static. Okay, when you heat the material, can also happen. Recovery can happen. Okay. So when you talk about dynamic recrystallization, okay, there are actually three different types of dynamic recrystallizations. There are three different types of dynamic recrystallization. One is called continuous dynamic recrystallization, CDRX. It's simply called CDRX, or discontinuous dynamic recrystallization, and the third one, geometric, dynamic recrystallization. Okay, so there are actually three different types of one actually continuous DRX, discontinuous DRX, and geometric DRX. Okay, so if we talk about continuous
There's
recrystallization,
some noise coming from your side.
Is it coming to everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Just 1 minute. How about now? Is it still
Now,
there?
okay.
Okay. So when you talk about dynamic recrystallization, there are three different types. One is continuous DRX, discontinuous DRX, and geometric DRX. So the continuous DRX is also called progressive transformation. Progressive transformation. What it means, okay, initially we do see recovery, then followed by a recrystallization, followed by a recrystallized, recrystallization is going to happen. For example, we take, a prior grain like this, so within a grains, within a grain, we do see subgrain formation, and these subgrains become with further deformation. With further deformation, these subgrains evolve into a full-fledged fine grains, full-fledged recrystallized grains. That means when I say recrystallized grain, it should have a high angle character. The boundary should have a high angle grain boundary character. Then only say recrystallized grain. Okay, that's the difference between subgrain and a recrystallized grain. Subgrains will be having low angle boundary grain boundary character, whereas fully recrystallized grain will have a high angle grain boundary character. So what happens with deformation in certain materials, at elevated temperature? So initially we do see recovery, dynamic recovery, followed by dynamic recrystallization. This is called extended recovery. This mechanism also called continuous DRX, or an extended recovery. Dynamic recovery is also called progressive transformation that is happening in a material during deformation. That is called continuous DRX. In case of discontinuous DRX, what happens? If you have a grain, prior grain, dislocations are there. Most of the dislocations are going to get generated, and get piled up or get generated around the boundaries. So what happens? There's a high energy here. So we do see formation of recrystallized grains along the boundaries, So this look like a necklace kind of structure. Look like a necklace kind of mechanism is going to take place. That means formation of fully recrystallized grains are going to happen in certain materials when you deform at elevated temperature. Okay, so along the boundaries, the formation of this necklace kind of recrystallized grains. Okay, if it happens, that is called discontinuous DRX. Okay, in case of geometric DRX, okay, when you go for a very large amount of strain, very large, okay, there is a large amount of strain, okay, when the grains, okay, for example, you have brown grain, okay, this kind of grain, very, if you get a very fine grain, okay, the elongated grain becomes finer and finer, width of the elongated grain becomes finer and finer. What happens? The size of the subgrain, okay, okay, if you compare, okay, we compare the size of this, okay, this prior grain, okay, if it is close to that, okay, two to three times of the subgrain size, that is called geometric DRX. Okay, about two grains of size, okay, that is called subgrain, okay, geometric DRX. This can happen when you deform material to very large strains, okay, very large strains. So when they see so much, okay, the reduction, okay, that can lead to the grain size is going to reduce. When the grain size, okay, the elongated grain size without the elongated grain becomes equivalent to one or two times of a subgrain size, that is called geometric DRX. Okay, so as far as dynamically deformation at elevated temperature is concerned, most materials can undergo either continuous DRX or a discontinuous DRX. Is it clear about?
Hello, sir.
Yes.
Sir, what kind of advantages can the discontinuous DRX provide over continuous DRX, or maybe vice versa?
There's no advantage. I said certain materials. Okay. So, for
Okay.
example, okay, this is something to do with the stacking fault energy. Okay. So, if we talk about high stacking fault energy and low stacking fault energy materials, okay, what is going to happen if, for example, if there is a high stacking fault energy material, okay, what kind of mechanism we are going to see first? The difference between, now if you take aluminum and copper, okay, aluminum is high stacking fault energy material, copper is a low stacking fault energy material, or low to medium stacking fault material. If you deform material, these two materials are elevated temperature, okay, one undergoes CDRX, other one undergoes DDRX. Okay, so now you know that, okay, effect of stacking fault energy. With increasing stacking fault energy, what happens? Cross slip or recovery. With increasing stacking fault energy,
Sir,
what happens?
work hardening won't happen in high
Recovery is
stacking
going to take
fault
place.
energy. Yes,
Recovery
sir.
can take place very easily because can cross slip very easily. Okay, that means there is a high possibility of having a recovery. Dislocation can get annihilated very fast in high stacking fault materials as compared to low stacking fault materials. That means recovery is going to happen already. Recovery is the first step which can happen in high stacking fault materials. Once recovery happens, okay, what that means when you say recovery happening means it's just subgrains are going to develop. Once subgrains develop, those subgrains only with further deformation will lead to a, okay, recrystallized grain structure. Okay, that is basically CDRX. In case of copper or brass kind of materials, low to medium stacking fault materials, what we see discontinuous DRX. What does it mean? Recovery will not happen very easily. Okay, in low stacking fault materials, the difficulty to cross slip is going to increase. Okay, cross slip will not happen. That more dislocations are going to get piled up or, okay, stored, okay, at the boundaries within the grain. Then we have enough energy for the recrystallization. There is enough driving force for the recrystallization to start before recovery can happen. Before recovery can happen, recrystallization can happen. Okay, so boundaries will have a large energy area. Okay, there's a lot of dislocation can get piled up or accumulated around the boundaries. So because of the high energy driving force which is available for a new grain to nucleate at the boundaries, that lead to a discontinuous DRX. Okay, so that is the difference. Okay, it's not advantage. Okay, it's a basically virtue, material property, material behavior itself. Okay, depending on stacking fault energy, we do see this kind of difference in the DRX mechanism. Is it clear?
Hello.
Yes, sir.
Yes. Yeah. Yes.
So this red hexagon is one grain or subgrain?
No, I'm telling. So this is now becoming a, okay, evolved fine grain. Okay, now evolved recrystallized
Single
grains.
grain.
Yeah, single grain, evolved recrystallized grain.
So discontinuous also is having a single grain.
Single grain. It's also because, but actually, you see, we look at it discontinuous. Here, actually, initially we have a subgrain. Okay, those subgrains become a high angle grain boundaries. Okay, fully recrystallized grains. Here, what happens? Here also we are nucleating recrystallized grain, having a high angle grain boundary character without any recovery.
And what is in between, say, this dislocation pileup between
These are
two grains?
dislocations. Some amount of dislocation, because initially what happens, where the grains are going to get nucleated, recrystallized grains going to get nucleated around the boundary because of
Boundary.
large dislocation. There will be some more dislocation will be there left out within the grain. Okay, slowly
Just
it evolves. Okay, so now it's what happens. Okay, I think we'll come to that. Okay. With respect, first we'll talk about continuous DRX. Okay, so okay, I think let me complete. What is, you have doubt? Any other doubt? First, you have any doubt?
Just
Yes.
Just one doubt, sir, means uh, for continuous, it seems easy that all the grains which are newly created with the subgrains is having a connection between each other. But in discontinuous, if we see the figure, it
No,
is
no,
showing a
just
necklace type of.
1 minute. I think just 1 minute. This is a prior grain. That means before deformation. This is a prior grain. Within a prior grain, there is elongation. We do see a elongated grain, okay, because of deformation. So within a grain, the prior step, okay, is basically before CDRX, there should be a recovery. There should be a recovery. That means subgrains have to form. And those subgrains, okay, with further deformation, convert
Will
into a
become fine grain.
recrystallized grain. Recrystallized grain.
Okay. So
Okay.
recovery followed by, recrystallization followed by recovery.
No. So what happens? First, initially recovery should happen. Okay. Those recover, when you say recover, means subgrains are forming. Those subgrains, okay, which will be having low angle character with more and more strain, large dislocations are going to get formed at the boundaries of a subgrains. Those subgrain boundaries become a high angle grain boundaries. Okay. Then we call it as a recrystallized grain. Then only we call it as a recrystallized grain. So subgrains will evolve into a recrystallized grains. In case of DDRX, directly we are actually initiating, okay, we are nucleating, okay, high angle grain boundary character grains at the high energy areas. So recovery is not the precedent step, okay, in DDRX. But in the extended recovery or continuous DRX, what you are talking about, recovery is the precedent step.
Okay.
Okay.
Understood, sir. Maybe in continuation it will get more clear with more further slides.
Yeah, continuous means actually in the first step should be recovery. Then
yes, understood.
Because already whatever energy is there, the driving forces come down now. We cannot nucleate recrystallized grains in high stacking faulted materials. In high stacking faulted materials, we cannot nucleate because driving force already has been consumed in the recovery process.
Okay.
So what is only thing, the way actually when you deform more and more, when you pump more and more strain, dislocations, so that basically lead to subgrain structure can convert into a high angle grain boundary character recrystallized grains. Okay. In discontinuous DRX, what I'm saying, in the low stacking faulted material, medium stacking faulted materials, the energy will be stored still, the driving force still available because recovery will not happen quickly. So the energy, whatever is there in the form of dislocation density, that can lead to a formation of a recrystallized grains directly without any recovery.
Okay. Understood, sir.
So this geometric DRX is observed only when very large strains. Okay, I think I don't spend much time. Okay, just introduce what are the different types of DRX. So when you talk about continuous DRX, okay, so the features, okay, initially, okay, there should be the curve, stress strain curve will be like, okay, what you are seeing a recovery and extended with more and more strain, it's going to get extended. Okay, that's why it's called extended recovery. The shape of the curve, okay, is going to be like this. So depending on temperature and strain rate, so with increasing temperature or decreasing strain rate, what happens? Your stress requirement is going to come down. Okay, the stress requirement for the recovery to happen is going to, what you are seeing. Okay, the recovery kind of CDRX thing, what you are seeing is basically lowers. The stress recovery is going to lower. At the same time, what happens initially, we are going to have a subgrains. Initially, we are going to have a subgrains. Subgrains will have a low misorientation angle. Okay, with more and more strain, we do see development of a high angle grain boundary. High angle grain boundaries are going to get generated. Okay, so if you look at here, the grain size, initial grain size, okay, we have very coarse grains, prior grains. When you deform it, okay, and with further deformation, we do see steady state kind of grain size is going to be developed. What is the effect of grain size? If you refine a grain size, now my starting grains, okay, one is actually 100 micrometers, other one is a 10 micrometer. Okay, the final grains is immaterial. Okay, what you are getting is the same. It's not going to be dependent on your initial grain size. Okay, the final grain size. Okay, though same material. Okay, aluminum. I've given an aluminum same material, only two different grain sizes. One is coarse grain. Okay, coarse grain size. Other one is a fine grain size. When the material deformed at elevated temperature, where there is a dynamic recovery is taking place and extended recovery is taking place, that lead to a same grain size at the end of the deformation. Okay, the grain size is the same. Grain size is same. Okay, that means the recrystallized grain that has come from extended recovery is actually same. Okay, whether it's a fine grain or coarse grain. So the mechanisms, what people have proposed, how a subgrain structure is going to convert into a high angle grain boundaries, grains of a high angle grain boundaries. So people, it can happen homogeneous, induced misorientation, or we may see lattice rotation based or micro shear bands. Okay, so the transformation of LAGBs, low angle grain boundaries, into high angle grain boundaries can happen by homogeneous increase of misorientation. Okay, homogeneously at all places can increase the misorientation. Okay, or by progressive lattice rotation. Progressive lattice rotation, there will be some kind of rotation can take place that can lead to a around the grain boundaries, that can also lead to conversion of LAGBs to high angle grain boundaries. Or it can also happen whenever there is a micro shear bands forms. So locally we do see there is a change in the grain boundary character. Okay, high angle grain boundary going to get generated. So these are three different ways, by which we can see formation of conversion of low angle grain boundaries into a high angle grain boundaries that lead to formation of a recrystallized grain under extended recovery conditions. Okay, is it clear about the CDRX?
Sir, in graph D, there are two curves.
Graph D.
D. Yes, sir,
Yes.
there are those two curves that are coming.
Yeah,
Could
the two curves of
explain
curve
those?
which grain size. Okay, D naught is a grain size. Okay, initial grain size. Okay, initially I started with this grain size. Okay, for example, one grain is 100 micrometers, other one is a 10 micrometer. When I deform both the material, same material composition, same, only grain size is different. Okay, what happens with strain? Okay, we are going to end up with the same grain size. So it's independent of your prior grain size. The recrystallized grain, whatever develops under CDRS conditions, the size is actually independent of prior grain size of the material. Okay.
Yes, sir, understood.
Sir, under different conditions, same material will show both continuous and discrete.
No, because it's a stacking fault energy thing. Okay, it's related to high stacking fault materials will undergo continuous dynamic recrystallization. Okay, if I take aluminum alloys, typically undergo CDRX. Okay, is it clear?
Sir, could you explain that part again where you said, like in CDRX, there'll be no nucleation, but in DDRX, there'll be nucleation. That part I
Yes.
didn't understand this.
See, if we talk about high stacking fault means low stacking fault end materials, high stacking fault end materials will undergo recovery fast. Okay, am I right? Because cross slip is very easy. So dislocation of
Yes, sir.
opposition can come together, can get annihilated very easily as compared to low stacking fault materials. Okay, so the driving force for recrystallization, we want to have a recrystallized grain we need to have some driving force, a new boundary to form. Okay, but already, because dislocate density is only the driving force supposed to be. Okay, but if you already dislocate density has come down because of recovery, so where is the driving force for recrystallization to happen in high stackable materials? Is there any driving force left out for
No, sir.
recrystallization to happen? Okay, first instead of recovery in high stackable materials, there's no driving force because recovery is the first step, can happen very easily. Okay, in high stackable materials, so dislocate density has come down. Okay, so there's no driving. In case of low stacking fault materials, recovery is very difficult. The cross slip is actually, the difficulty of cross slip is going to increase with decreasing the stacking fault energy. That means you can store large amount of dislocations in a low stacking fault materials. If a large amount of dislocations are stored, usually most of the times more dislocations can stored near the boundaries most of the times, which are high energy areas. Okay, now we have a driving force for the recrystallization to happen. Okay, because dislocation has not, it's not come down, it's still we are increasing. So that can lead to a fresh nuclei can form, a strain-free grain can form, okay, which is of a high-angle grain boundary character. If a strain-free grain forms with a high-angle grain boundary character, that is called recrystallized grain. Okay. So this is the kind of, the difference because of stacking fault energy difference. We do see the way the final recrystallized grain, strain-free grain with a high-angle grain boundary character, how it is developing, okay, is going to depend on stacking fault energy material. Higher the stacking fault energy, we do see first recovery followed by a recrystallization. Okay, if you got low stacking fault images, directly we do see formation of a recrystallized grains. Clear now? Is it?
Yes, sir. Yes, sir. Sir, so nucleation means the formation of new recrystallized grain, right?
Grain, yes.
Okay, okay, sir. Understood.
Sir, when we talk about the final grain size of the recrystallized grains, so what are the parameters? Like, is it constant for a particular material, or can we tweak it by using like first process parameters? Like how to control the dislocation cell size?
Yeah, because stacking fault energy by alloying, okay, because this is how it will be usually, okay, we already discussed, okay, how to control the subgrain size, cell size. Okay, once you control smaller grain size, smaller cell size, you can help you smaller grain size. Okay, and if you go for higher and higher temperature, there will be growth. Okay, recrystallization also has nucleation plus growth, so there will be again increased grain growth. Okay, so one has to play with the temperature strain rate also. Okay, if you want to get, okay, because we know that higher the large with increasing strain, typically cell size decrease, it becomes a steady state. That was the thing we had first 2 or 3rd lecture, 4th lecture. Okay, your subgrain size is going to get saturated in a material. Beyond that, you don't get, okay, because there is a subgrain size is depending on your stress requirement. Okay, lower the stress, higher the subgrain. Okay, that's we already discussed. Okay, so depending on temperature, strain rate combination, and with the material in a fixed material, we do get a particular subgrain size. Okay, so the subgrain size basically depends on a stress. The stress basically depends on all of the parameters, with temperature, strain rate. Okay, so lower the stress, typically higher the subgrain. Typically, we do see. Okay,
Yes.
one can calculate, okay, for a given material what is the subgrain size. In that, I think in the previous lecture I showed, okay, D is equal to 20 GB by sigma. Okay, so sigma, because your D okay, D what you lambda, because lambda means subgrain size, lambda is inversely proportional to sigma, and sigma is going to depend several other parameters.
Yes. Sir, also when we talk about this discontinuous dynamic recrystallization, so it is
I'm yet to come to this, okay, discontinuous, just like a continuous dynamic recrystallization. Okay.
Yeah.
Okay. Next slide is basically related to discontinuous dynamic recrystallization. So this basically, okay, it has a characteristic feature in stress time curve. Okay. Okay, if we talk about CDRX, it's just simply we see like a DRV, okay, dynamic recovery kind of curve. But in case of a discontinuous dynamic recrystallization, okay, it is a strain hardening, okay, work hardening kind of thing. When there is a, okay, DRX, okay, if it is a discontinuous DRX, we can see there is a peak followed by a drop in stress, then again a steady stress. Okay, or we may also see some serrations in a stress strain curve. Okay, then followed by some steady stress. Okay, so when I say discontinuous dynamic recrystallization, usually the nucleation of recrystallized grain is going to happen along the boundaries. Okay, with more and more strain, okay, we do see formation of more of such, okay, grains, recrystallized grains in a material. So this dotted lines, what you're seeing is a prior grain. This is my prior grain. So with the deformation, with more and more deformation, what happens? Okay, initially there will be a recrystallization going to initiate at some temperature. There's an onset, okay, critical strain required for, okay, recrystallization to take place, because we need to give some amount of drying force. Then only we do see formation of recrystallized grains. So these recrystallized grains, more and more recrystallized grains are going to form with further deformation, with further more and more deformation. Okay, that can lead to a fully recrystallized grain structure. Okay, so if I look at here, okay, the amount of recrystallized fraction, how much recrystallized fraction is taking place, is basically going to depend on strain. Okay, with increasing strain, we require some critical, okay, strain. After that, with increasing strain, the recrystallized fraction can going to increase, can increase with strain. It is going to depend on temperature, strain rate, and your initial grain size. Okay, for example, initial I have, okay, so with decreasing temperature, okay, changing this curve is going to change like this. That means at a given strain, if I fix the strain at a given strain, if the temperature is high, okay, we are going to see more recrystallized fraction. Okay, if the strain rate is low, okay, we are going to see more recrystallized fraction. Okay, if the grain size is finer, we are going to see more recrystallized grains.
So fraction means as against original
Fraction.
grains?
No. Forget about. Now see, for example, okay, you have, this is a, what happened with A to D, the fraction of recrystallized grain increased or decreased?
It is increasing.
Yeah, that's called fraction. Okay. Only just
Yeah,
we are
means
considering, well, okay, yeah, with respect to your prior, okay, how you have
prior,
this much
yes.
volume of material. Okay.
Okay.
So in the particular volume, now we defining, okay, your recrystallized
Okay,
grain is particular
percentage of
size.
space that they are taking,
Yes.
or
Yeah.
percentage of
Volume fraction.
okay.
Okay. Volume fraction, or okay, area fraction of a grain.
Okay.
Okay, so the recrystallized fraction can become, okay, 0 to 1. Okay, that means it's like 1 to 100% can happen. Okay, it's basically depending on strain. Okay, usually with increasing strain, the recrystallization fraction is going to increase, and it is going to depend on temperature, strain rate, and initial grain size, the amount of fraction what we are seeing. Okay, so at a given strain, okay, okay, if you have high temperature, low strain rate, and fine grain size, can lead to a higher recrystallized fraction. Okay, is it clear? Okay, so I said there's a typical, okay, stress strain curve. We do see a material which undergoes DDRX. Okay, initially we do see a strain hardening, then there is a peak stress followed by a drop in stress, then gets saturated, gets, okay, steady, becomes a steady state. Okay, so we get a steady state stress with strain. I said, okay, there is a critical strain at which recrystallization DRX is going to get started. That is called epsilon C. Okay, at a critical strain, the recrystallization is going to get initiated. Okay, then there is a peak stress. Okay, afterwards, okay, your recrystallization fraction is going to increase. Recrystallization fraction is going to increase. Okay, after certain amount of strain, we do see a steady, okay, state. Okay, steady state is going to get established. Okay, so the critical strain, okay, typically, okay, about, okay, 0.8 to 0.9 times of, okay, epsilon p for most metallic materials. Okay, the critical strain is about 0.8 to 0.9 times of epsilon p. Okay, because epsilon p can be known very easily, because there is a peak stress. Okay, at the peak stress, what is corresponding strain? Okay, once I know epsilon p, at what strain is going to get initiated, basically around 0.8 to 0.9 times of, okay, so at that strain, okay, there is a recrystallization going to get initiated. Okay, now we can know what is the degree of recrystallization without looking at microstructure, by based on this stress strain curve. I can estimate degree of recrystallization. I can estimate what is the degree of recrystallization, what is the volume fraction of recrystallization. Okay, so there are two things. People use degree of recrystallization and volume fraction of a recrystallization just from a stress strain data. Without looking into the microstructure, one can actually establish how much, what is the degree of recrystallization and how much volume fraction of a recrystallization taking place. Okay, this is how people do. Okay, degree of recrystallization. Okay, at any given, for example, at a particular, if I want a particular strain, what is my degree of recrystallization? If I want to know what I should do, because it's nothing but sigma minus sigma p. Okay, sigma minus at a given stress, sigma minus sigma p by sigma s minus sigma p. Okay, that this ratio is basically indicates degree of recrystallization, DRX, that's happening during deformation. Okay, and if we talk about volume fraction of DRX, people use Arrhenius type of equation. Okay, where the volume fraction of DRX can be expressed 1 minus exponential minus AD. Okay, AD is a constant and D is a constant, material constant. Epsilon minus epsilon C by epsilon star. Epsilon minus epsilon C by epsilon star. So at a given strain, what is the volume fraction of DRX? Okay, one can establish using this equation. Okay, one actually we have to know epsilon C and epsilon star. Epsilon C is a critical strain for DRX that can be known from a peak strain. The strain corresponding to peak stress, we can know what is epsilon. From that we can know epsilon C and epsilon star. Okay, it basically tells strain for maximum softening rate, the strain at which maximum softening rate is happening, the strain at which maximum softening rate is happening. Okay, if I know this epsilon C and epsilon star, I can know at a given strain what is my volume fraction of a DRX, dynamically recrystallized grains fraction. Okay, is it clear? Hello,
Sir.
is it clear about?
Yes, sir. It is
Okay.
clear.
Okay, without looking at microstructures, if I have this typical characteristic stress strain curve, one can actually know what is the degree of recrystallization and degree of or volume fraction of DRX. Okay, dynamic recrystallized grain fraction can be estimated at any given strain. Okay, so once you get once it becomes 100% recrystallized grain structure, then basically we get a study. Okay, so it becomes a 100%. Okay, if we talk about the ratio, okay, it becomes a 100%. Okay, so how do you, because you have to know, if I want to know volume fraction of recrystallized grain fraction, I need to have epsilon C, can be known very easily. How do you get epsilon star? Because I want to know the strain at which maximum softening rate is taking place. How do you get epsilon star? Because from this curve, how do you get epsilon star? Any guess?
Slope, I guess.
Yeah,
with
we
the
need to take a work hardening. We have to make a plot. Okay, theta is equal to d epsilon by d. Okay, epsilon as a function of strain. If you make or a stress. Okay, for example, we have a stress strain curve like this. Okay, this is the effect of deformation temperature and effect of strain that we get this kind of stress strain curve in a particular steel. It was established. Okay, if I make a plot for this stress strain curve, if I make a plot theta versus sigma, okay, or theta versus epsilon, okay, we do get a, there is a maximum softening. Okay, that means theta becomes a negative. Where is the maximum softening? That's basically maximum softening means maximum maximum magnitude in negative value. Okay, that correspond the stress we get from the corresponding stress, we can get what is the strain. So that basically gives you strain for maximum softening rate. And epsilon p basically the peak where the d sigma of d epsilon equals 0. When if we get a peak, that's a slope is 0. D sigma d epsilon equals 0. Okay, epsilon p will get it. Once you know epsilon p, you can know what is the epsilon c. Okay, so this is how actually people use stress strain information to understand and estimate what is the DRX fraction or degree of DRX in the material. Okay. Any doubts here? Okay, so the discontinuous dynamic recrystallization, okay, we said we may see a single peak or a some kind of oscillations in a stress strain curve followed by a steady. Okay, so there is a peak followed by a drop in stress, then again steady, saturated stress, or we may see some serrations in the material. It is going to depend on your parameters like a temperature and strain rate. With increasing temperature and decreasing strain rate, we may see these oscillations in the curve. Okay. Or similarly, with refining grain size, coarse grain and fine grain, okay, we do see this kind of with the refining grain size, we may see oscillations in the stress strain curve. Okay. So, in order to account both temperature and strain rate, we use Z. What is Z here? Can anybody say? You are basically taking into account of both strain rate and temperature effect. What is Z?
General
General
General Holloman parameter, okay, which basically accounts both strain rate and temperature. Okay, so that means depending on Z and your prior grain size, okay, you may see the type of curve, the stress strain curve what you are seeing can vary. Okay, so one can actually make a master plot. Okay, Z versus initial grain size, Okay, so typically there is a boundary. Okay, there is a boundary. Okay, is established for a given material. Okay, so what does it mean? Okay, at a given initial grain size, okay, higher Z, higher Z lead to a single peak, lower Z leads to multiple peaks. When I say lower Z, that means lower strain rate or higher temperature. Okay, lower strain rate or higher temperature can lead to a multiple peaks. Okay, lower Z. Okay, higher Z can lead to a single peak in a DRX called stress strain curve of the material. Okay, similarly, if I fix the temperature and strain rate, okay, if the grain size is finer, the initial grain size is finer, okay, we do see multiple peaks. If the grain size is finer, we do see multiple peaks in stress strain curve. If the grain size is coarser, okay, initial grain size is coarser, okay, we do get a single peak. Okay, that's one. Okay, the second thing, okay, if I see a single peak, we do see final grain size what you are going to get a refinement. The grain size is going to get refined. Okay, under DRX conditions. If okay, if the conditions such a way that you here if it falls within this window, that can lead to a grain coarsening. Okay, so if I take fine grain size and coarse grain size, initial grain size, the coarse grain size can lead to a refinement and get a some steady grain size. Then if you take a coarse fine grain size, fine grain material, okay, we usually some kind of coarsening is going to take place, then can lead to a steady kind of grain size. Okay, similarly, if you talk about temperature and strain rate effect, okay, we started with same grain size. Okay, assume, okay, we may see with increasing strain, okay, we may see grain refinement or grain coarsening. Okay, when I say when the decreasing temperature, increasing strain rate, what is meaning of Z? Z is basically higher. Okay, with increasing Z, okay, we do see a grain refinement in the material. Okay, after strain, okay, whenever there is a DRX happens, okay, the finer grain size is going to be finer, okay, at a higher Z values, or fine, in a fine. For example, if you look at here, okay, when you look at fine grains, there's no dependence. Finally, you're getting the same grain size here, but here, okay, what we are seeing, the Z effect, okay, is going to be dominant. That can influence. It can be a fine grains. It can be final grains is what you're getting can be finer or coarser depending on Z value. Okay, is it clear? Any doubts here?
Sir, in that last image, we are increasing Z value, sir. Is this
Increasing Z value. Okay, Because when, for example, the strain rate increasing or decreasing temperature,
Yes, sir.
basically jet is increasing. Okay. Okay, at a initial particular grain size, if you start with a particular grain size, okay, you start with a particular grain size, higher jet lead to a grain refinement than the low jet value.
So it means that we do the deformation at lower temperature with a higher strain rate, we can get fine grains. Like
Yes. Okay. So any doubts here? Is it clear?
yes, sir.
So what is the meaning of, okay, why you are getting multiple, okay, peaks? What does it mean? Because test tank was showing multiple peaks. What is it represents? What does it represent?
Sir, multiple recrystallization cycles occurs. So
Yeah, the cycles basically initially you're right. Okay, the material, okay, is going to get complete recrystallization by end of this thing. Okay, again we are going to see again hardening. Okay, again recrystallization. Okay, again hardening and recrystallization. Okay, these are multiple recrystallization. That means, okay, here in this case, okay, the microstructure is a partly recrystallized. Partly recrystallized. Okay, after certain amount of deformation, fully recrystallization happens. Okay, so that's what happens if we take a coarse grain and fine grain, fine grain. Okay, in a coarse grain, okay, the boundaries are less as compared to fine grain. Okay, so the recrystallization happens, okay, randomly at, okay, only at certain boundaries. Okay, here multiple recrystallization can happen. Okay, so complete recrystallization can happen if there is a fine grain size, because a lot of grain boundaries are there. So multiple, okay, same at same time, okay, recrystallization can happen, can get completed. Then again, we do see work hardening of those recrystallized grains. Again, okay, it's like the cycle happens in a fine grain system. In coarse grain material, it is going to, okay, partly getting recrystallized, and we have a deformation, then slowly is expanding. The recrystal fraction is going to increase. After a certain time, then it becomes to get saturated. Okay. That means everything, fully recrystallized happens. Okay. So that's what the effect of, okay, temperate grain size and prior grain size and the, okay, jet values. Okay, so when you see this multiple peaks, means actually multiple recrystallization happening. That means actually complete recrystallization happening, followed by again work hardening, again recrystallization. Okay, after certain amount of time, we do see balancing. Okay, so finally we get a, okay, steady stress. Okay, so depending on your initial grain size and temperature and strain rate of deformation, we do see changes in a stress strain curve. Okay, which if the material is exhibiting dynamic recrystallization. Okay, is it clear?
Hello,
About,
sir.
yes.
Sir, is this in any way related to the DSA serrated flow behavior that we studied,
No,
or
no, no,
not?
no, no. It's nothing to do with that. That's what. Okay.
Okay,
That's what I
okay.
check. This serration, even if you remember there, serrations can be seen. Okay, different things. Okay, when there is a twinning, when there is a dynamic recrystallization. Okay, apart from what we are seeing DSA. Okay, this is a high temperature phenomenon. Okay, where at this temperature we don't see. Okay, kind of, okay, pinning and unpinning action. Okay, high temperature. Okay, very high. Okay, this is temperature you're talking 0.5 times the melting point above. Okay, it's nothing to do with it. Okay, that's what one slide I showed you. Okay, what conditions we do see serrations in the stress strain curves. This is one of the things can also represent stress strain curves. Okay, the stress strain curve can have a serrations apart from DSA. Okay, twinning,
Yes, sir.
phase transformation. Those things, okay, can give rise. Okay, this kind of serrations. Any other doubts? Okay, so typically, okay, if I talk about discontinuous dynamic recrystallization, the grain size, the average grain size, what you get, okay, the final grain, what you are seeing, look at here, the recrystallized grain size is almost, okay, constant. Okay, that means, okay, you get almost nearly same recrystallized grains, even, okay, when it becomes 100% recrystallization. Okay. So there is a law called Derby law, which basically tells, okay, the average, the or mean grain size of a recrystallized grain during dynamic recrystallization is basically going to depend on Z. Going to depend on Z. Z is basically general Hanuman parameter. Okay, lower the Z, okay, your grain size is going to be, okay, lower the Z, Grain size is going to be coarse or finer?
So lower the jet, coarser the grains.
This is inversely proportional. Okay, D is inversely proportional to Z. Okay, you get a coarse grain. Okay, if the Z is okay high, you get a fine grain size. Okay, so this is how okay people have established after looking at various okay materials. So especially for steels, it was well established. Okay, the mean grain size of recrystallized grain is basically going to depend on Z. It is almost independent of your initial grain size. Independent of initial, that will get a saturated same grain size you're going to get. Okay, unlike static recrystallization, the mean size of dynamic recrystallization okay does not change as recrystallization proceeds. Okay, in case of static recrystallization, what happens? Whatever recrystallized grain formed is going to grow under static conditions, but under dynamic conditions, we don't see those grains are going to grow because we do see a lot of pinning action. Okay, because during deformation, whatever recrystallized grains are formed, those grains are going to retain. Okay, the size of the grain is going to be almost same under dynamic recrystallization conditions, unlike a static recrystallization process. Okay. So this is what okay about continuous DRX and discontinuous DRX. So typically there are mechanisms for recrystallization. Okay, so how the recrystallization is going to happen? Okay, in a material. So we already discussed some of them. Okay, but if we talk about there are three well-known mechanisms. One, subgrain formation and subgrain boundary migration. Okay, so usually okay the mechanism says okay we have a subgrain formation, subgrains are going to form, and these subgrains okay the boundaries of subgrains can migrate. Okay, that can lead to a high angle grain boundary character. Okay, so this becomes a recrystallized grain. Okay, so this can happen okay in okay typically because it's static, most of the times this will happen during static okay static recrystallization process. This mechanism is applicable under static recrystallization. What happens okay, when you deform material to very high strains okay and heat it to high temperatures okay we do see low stacking for materials. In this case we do see formation of a subgrain okay and subgrain boundary migration can take place. That okay when there is a subgrain boundary migration take place, that can become a fully recrystallized grain. Fully recrystallized grain. Okay, so this mechanism is mostly people actually seen in low stacking value materials and alloys. There's another mechanism, subgrain rotation and coalescence. Subgrain rotation and coalescence. What does it mean? We have subgrains already. Okay, subgrains have been formed because of recovery process, because of a recovery process. So these subgrains are going to get rotated, okay, with some thermal energy or some deformation. During deformation, we may see these subgrains are going to rotate each other, can become a kind of okay subgrain, full grain, okay, fully recursive. It becomes a fully recursive again with almost high angle grain boundary character. Okay, so this mechanism has been seen in high stacking fault energy materials. In high stacking fault materials, we deform material to very large amount of strain, and if we heat it, you heat the material. Okay, what happens? The subgrains, whatever okay, the initial cell structure can be converted to subgrains. That's recovery. Then once subgrains form, they can get rotated. Okay, rotation happens and get coalescence. Okay, can lead to a now high angle kind of boundary. Okay, grain with a high angle grain boundary. So this is called fully recrystallized grain. Okay, so this is basically okay happens in a high stack for materials and alloys. Okay, these are kind of okay, which can lead to a subgrain coalescence in the material. So there's another important mechanism which happens during deformation. When you deform material at high temperature during hot deformation, the important mechanism is called strain-induced boundary migration. Strain-induced boundary migration is called SIBM. SI, simply called SIBM, people call it's a strain-induced boundary migration. What does it mean? Okay, here, for example, we consider there are two grains, okay, grain 1 and grain 2, and it has a respect to change in energy because of dislocation density is different. The grain, okay, 1 has a different dislocation density as compared to grain 2 because of orientation effect. We may see the deformation of grain 1 will be different than the grain 2. Assume that the energy stored, okay, in the grain 2 is higher than the grain 1. Grain 1. So what happens? The boundary which is between this, okay, grain 1, grain 2, okay, we do see a bulging, okay, some bulging kind of thing is going to take place. So this bulging of a boundary, okay, is going to take place at the because of energy difference. At the same time, because of difference in energy, okay, your subgrains whatever form in a grain 1, the size of a subgrain what it forms is different than the size of subgrain it can form in the grain 2. Look at here, schematically it's shown, okay, it has low energy grain, has a relatively coarser subgrain, whereas high energy grain has a relatively finer subgrain. Okay, so at the interface between these two grains, okay, we do see, okay, change of, okay, the subgrain structure is going to be like this, then becomes a, okay, a fully, okay, strain free grain, becomes a strain free grain without any subgrains, without any subgrains. Okay, so during, okay, with further deformation for the heat, okay, what happens, the subgrains are going to grow, okay, at the same time we are going to see formation of a strain free grain at the boundary. Okay, so this is how actually people explain, okay, the formation of a recrystallized grain, okay, due to difference in the energy between the grains. Okay, so that can lead to formation of, okay, this is called strain induced boundary migration, because the difference in strain can lead to difference in energy, so that can induce a boundary. Okay, there's a kind of bulging kind of thing happen because of difference. So this finally lead to a formation of a strain free grain with a high angle grain boundary character. So this, okay, requires very small amount of strain is good enough. Okay, less than 40% of strain is good enough. So that's why actually during hard deformation, about, okay, small amount of strain, okay, 20% 30% strain itself, we can see formation of a recrystallized grain. Okay, so these are the type of, okay, different types of mechanisms. There are various mechanisms people have put forward, but well-known mechanisms what I've given, actually one, actually subgrain formation followed by a subgrain boundary migration, subgrain boundary migration. The second one, subgrain formation, rotation, and coalescence. That's the second mechanism. The third one, strain-induced boundary migration. Okay, it's very well-known equation which was developed. Okay, I think almost like later than those two mechanisms, and this has been widely accepted mechanism during hot working. When you deform material at high temperature, whatever DRX what you are seeing, okay, it can be, okay, due to this kind of formation of a subgrain, formation of a recrystallized grain with high angle grain boundary character due to difference in energy between the grains. Okay, so this is a kind of, okay, whatever, okay, this is actually applicable even static recrystallization also. Whatever mechanism mentioned, those can happen even during static recrystallization. Some of this can also happen during, okay, dynamic recrystallization, but depends on the stacking fault energy of materials. Okay, is it clear? Any doubts?
Yes, sir.
Are there any doubts? Okay.
No, sir.
Yeah, so I'll stop it here because this is what I wanted to discuss under dynamic deformation, okay, activities. Okay, so we had, okay, during dynamic, when you deform material dynamically, the recrystallization, okay, you do see dislocations are going to get generated, get multiplied. All those things we already discussed. Okay, what I discussed in this today's lecture, basically at high elevated temperatures, okay, what kind of changes are going to happen. Okay, so the restoration is going to happen. Grain structure is going to get restored. Okay, that basically the resource mechanism with DRV and DRX. So we had discussion about how the DRV is going to take place and what are different types of DRX and how recrystallization can happen in a material, okay, in a deformed material. Okay, so if there are any doubts, please let me know. I'll stop it here. So I'll stop recording, I think. Okay.